Good evening, everybody. I guess we could call this a non-standard logarithm problem. We can make it a little bit easier. Mainly, it's just the symbols we're using are fairly non-common or non-conventional, I guess. But let's do log. We'll just use the standard notation here. B is a common representation for base. And that it's often the case that the parentheses get omitted. I'm going to go ahead and put them in. Okay, equals to y. And this proves that a logarithm is an exponent. A logarithm is an exponent just by the way the definition looks. And well, actually, we haven't gotten far enough to say that, have we? But this is true, or it's absolutely equivalent to this statement right here: b raised to the y equals to x. Okay. So again, a logarithm is literally an exponent. That's why all those properties you see that looks like exponent laws are understandable, because of it's the inverse function of the exponential function. Okay, this reads log base b of x is equal to y if and only if b raised to the y is equal to x. Now that's going to be useful to help us rewrite this object in an equivalent form that's amenable to the laws of exponents. And so that's exactly what I did right here. If you'll just take a look at this definition, and what I've done right here, it's precisely what this says right here. Okay. Now the rest of it, a lot of the rest of it is just laws of exponents. One thing that is important here is this connection between rational exponents. And this actually is quite confusing right here for a lot of people. It was for me. I remember in middle school even. Everybody leaves out the 1 and the 2, okay? But you see how that pops into play over here in the rational exponent representation of the symbol. And the very same thing over here, 1 and 5, index of the, but that's why this is particularly confusing to beginners, and it's to some people who've been doing math for a while. But you can see how this is all playing out. We rewrite it because there's some laws of exponents. The one in particular would be b to the m raised to the k is equal to the product. And this has a nice combinatoric ring to it. You multiply the exponents together precisely because you can literally say it. There are k copies of m copies of b. So there's m times k copies. And that's exactly what we do right here. If you just take a look at this statement, from here down to here, you see how we multiplied this exponent against 1/5 to get this statement right here. Okay, in a similar fashion, we multiplied this exponent 1/2 times n over 28 to get this statement. And it gets fairly easy from here because we know now. Notice that. Oh yeah, another important rule that actually popped up here. Is b raised to the minus n. And these are all very provable results. I won't take the time. It doesn't take that long actually, but I'm not gonna spend the time proving it. But this is true for all natural numbers. Okay, I guess it's true. Trivially true for n equals 0 also. Okay, and for all integers, I guess. Okay, but notice that it doesn't work. If you take a look here, there's no nice answer. Like, for example, what would it take to have 31? You see, we need a 31 to happen, and we need the n. What would that be? 33. We need, 44? We would need a 44 right here, right? We would need 44 right here. 44 for n minus 13 gives us 31, but it doesn't work out for the 5. If you put 44 right here, you get 16 over 5, which is not equal to 5, right? So it turns out to be quite useful to use this property here twice, actually. You see how we invert? And probably this problem worked out this way because this base is actually a little less than 1. Notice that the fit through to 31 is a little bit less than 2. And this number is a little bit bigger than 2. And so you get that this base is actually, let me write it right here, it's less than 1. And actually, this is an interesting base all by itself. I'm going to do another video on that. But negative bases that are between 0 and 1 have a completely different behavior. They don't look like the normal logarithm graph. But I won't delve into that too much. But anyway, right here, what do if we reverse this? What do we need right here for our n? Well, we need n equals 18. Now, I'll write it down temporarily, but you can check that n equals 18 works. See, this avoids, you can just check. You can kind of guess and check here in a legitimate sort of way. We saw it didn't work in this scenario, so we applied this law of exponents. And we see that n equals 18 gives us a 31 right here, but it also gives us 18 minus 28 is negative 10 over 5 is negative 2, right? And you, of course, you have to check to see if it works here. If you put, right down here, if you put n equals 18 right here, you get 18 minus 13 is the 5 that you see right here. And if you put n equals 18 right here, you get negative 10 over 2, which is negative 5, right? So n equals 18 works by inspection. Totally legitimate process here, okay? And I did this because I actually had concrete numbers in there, and I noticed these relationships and made up the problem. So, I mean, in a manner of speaking, I knew what to look for. But this is something you could find on your own without having authored the problem, okay? But I got n equals 18. Let me know if I didn't check. I'm not saying this is the only answer. I kind of think it is. The logarithm function this one's a little bit different. It's actually positive between 0 and 1. In a logarithm with a base greater than 1 is negative between 0 and 1. So that's in a whole other video and a whole other question type. But anyway, I did get n equals 18 for the solution, folks. So let me know if I did anything wrong or if you got the same thing. Okay, and again, you could probably formally have found this answer, but it's just too easy to do by inspection with these prominent bases right here, 5, 31, and 5. The hang up would be knowing to rewrite it like this, you know, probably if you got stumped right here. Okay, that's all.